In this classroom, unlike the other classroom, does not have a mic and a speaker, but the other classroom has an amplifier. So I don't know why. Could be. Who's teaching in that classroom? Okay. All right. So let's see. We left off last time talking about the number wheel. And did we talk about negative number representation and how to flip numbers to its negative side?
We were discussing that we could move past 0 on our number wheel to get negative numbers.
Okay. So that's what I recalled as well. I just didn't know how far we got with the number wheel. All right. So what we're going to do today is to talk about once we know the representation, what can we do to invert the sign of values? But when we're already using binary numbers to represent assigned values. Is that okay? Are there any questions about what we are about to talk about today? So we talked about, okay, let me go back to the notes first so that I can remind you what we talked about last time regarding how we represent negative values. Okay. All right. I know you cannot see anything yet. I'm just getting to the number wheel so we can start to talk about that. Okay, so here's the number wheel. Start this up. It's starting up just really slow. There we go. All right. So it should display the number wheel in a few seconds once the USB is starting to talk. Yep, I clicked OK already. Could be. Okay, let's try it one more time. Nope. Okay. Oh, it's still installing a Visor APK, so they probably have an update. That's why. Great. There's so many different pieces to the whole thing.
It's gonna log you out. Crash me.
Well, it's already installed, but the fact that it is quote unquote installing the Visor APK means the package has been recently updated. And it doesn't show anything on this side. Everything on this side looks good. Yep.
Well, we're connecting now.
Yep. So it's just finishing the installation. Okay, let me click the other button. There we go. Woohoo! All right. Well, it does work. It's just a little bit slow. Okay, so you guys do remember the number wheel? Just focus on the center part. Okay. So what we're doing is we are using 4 bits. Okay, in this case, 4 individual binary digits to represent values. So we can represent just the unsigned values, things that are not negative. If that is what you want to do, then you can follow this 0 all the way to 8, 9, and all the way to 15. So we can represent individual values from 0 to 15 if you say, oh, I don't need to represent assigned values. We don't need to represent anything negative. Then you can use up every single bit pattern to represent non-negative values. On the other hand, if you look at your application, your program, and you go like, well, I kind of need to represent negative values, then what we're going to do is to say, oh, 1 notch counterclockwise from 1 is 0. okay? So it seems like counterclockwise is going to a smaller value. So when you go from 0, one slot counterclockwise, then you can get -1. Then you get -2, -3, -4, -5, -6, -7, and then we have -8. So that's how we assign the representation, like 1100 is now used to represent the value of -4. Is that okay? So this is really just an assignment, okay? You know, the math does work out really well behind the scene, but you have to remember we are really just saying, okay, 1100 is now representing the value of -4. Is that okay? I think I also talked about when it matters and when it does not matter, whether we are dealing with signed versus unsigned values. When we are adding and subtracting, it really doesn't matter. It works out either way. But when we are comparing, then it really matters, okay? Because you have one bit pattern, say 1111 on one side, and you have another bit pattern 0000 on the other side, and your program says, if this value is greater than the other value, then we need to go here, otherwise we go there, okay? A typical conditional statement or if statement. Then it really matters, because now you have to ask, should I consider 1111 as -1? Because in that case, -1 is less than 0. Or should I consider 1111 as 15, which is not less than 0? So then it matters, okay? When you're comparing, then it matters. Okay, so what we'll do today is to first we'll go over, how do we change, if I give you the bit pattern of 4, okay? How do you figure out the bit pattern of -4 when we have already decided that we want a signed representation? If I already give you the representation of 1011, which is representing -5, how do we find the representation of the negation of that, which is 5? So that's what we'll start with, and then we'll see how much time we have, and then hopefully we can get to comparison at some point today. So is that okay so far? Okay, I'll be connecting back to what we talked about last Wednesday. All right, cool. And this is one thing I really don't like about having 2 instruction days per week is, we got too much time in between, like 5 days in between. So unless you guys really are diligent to kind of study and revisit what we talked about last time, it takes a little bit of time to reconnect to the concept that we talked about in the previous class. All right, so I'm gonna let me just kind of copy and paste that number wheel because it's really useful in today's discussion. So I'm gonna copy and paste it, which is something that I can do with this tool. So we just need to get the box cutter. Okay, and then we copy, scroll all the way to the end, right about here, and then we paste. Uh-oh. How do I, oh, there we go. Nope, that's layers. I must be missing something. How do I paste? Uh-oh. Tab cannot operate a computer. Okay. So we copy. And then the check is pasting already, which is not what I want to do now. Undo. Okay, so we copy. There we go. Okay, there we go. Now we paste. Okay. So what we want to do is to figure out a pattern, okay? So instead of giving you the definition, the bit operations to flip the sign of a number, I want you guys to work with me to figure out what pattern it is and how to solve that problem. Is that okay? So what do you notice as a pattern here about the negative values, and what do you notice? Do you notice anything about between the signed versus the unsigned representation? That 15 and -1 have the same binary representation. 14 and -2 has the same binary representation. And 13 and -3, 12 and -4. Do you notice a pattern? Yes?
You could add those two numbers or the absolute values to get 16.
Yes. So when you add up the absolute value, you get 16. Which also means if you subtract one from the other, you get 16. If you subtract the negative value from the signed, if you subtract the signed value from the unsigned value, you get 16. Is that making any sense? Okay. It is also telling you that you have to kind of walk this way. How many times? If you walk 3 times, 1, 2, 3, you get -3. But this is also 16 minus 3, 13. So it looks like, that is what we need to do. Okay. So I'm going to write on the side here. If you are given, can switch the tool back. So if you're given x as a 4-bit number, okay, what we notice is 16 minus x is going to give us the negation, okay, the binary representation of the negation of x. Okay, let me write it down here. Okay, the bit pattern of 16 minus x is the representation of negative x, or the negation of x. Well, let's try this out a few times and see whether this is nonsense or whether it works or not, because the next few operations will hinge on this being correct. Okay? So what we'll do is, instead of theoretically asking a question, we'll just try out actual things. Okay? So we'll say, what if x is 5? Okay? When x is 5, then we want to compute 16 minus 5. Okay? So we claim that negative x is 16 minus 5, and that turns out to be 11. They go like 11 is not a negative value, but it does share the representation of a negative value. Which negative value are we talking about? The value of -5. All right. So I'm using equal here, but kind of in a kind of vague way, okay? But they share the same representation. So 16 minus 5 seems to work. Let's check out the other way around, okay? What if I give you a negative value and see whether this works or not? So let's say x is -3. So we say the negation of x is 16 minus -3, which is supposed to be 19. But 19 is not even here. So where do you think 19 should go? The 0 is 16, 17, 18, 19. So that turns out to be 0, 0, 1, 1, which is actually the representation of 3. So the idea is this question mark here, not this question mark, this equal sign, and this equal sign here is looking at equality, but from the perspective of modulo math. We are modding everything by 16. If you mod 19 by 16, you get 3. If you mod 11 by 16, you can potentially get -5. It's the same thing. Is that okay so far? All right? Okay, so that's not too bad. All we have to do is to do a subtraction from 16. And we know how to do 4-bit subtraction already. There's one small problem here. 16 does not fit into a 4-bit number. It has got 5 bits. It's 1 followed by 4 zeros. So it doesn't fit. Okay? So then what do we do? So we look at the math, and we go like, okay, so we're looking at 16 minus x. But we cannot do 16 because we cannot represent 16 as a 4-bit number. If you only have a 4-bit subtractor, everything has to be 4-bit operations. And we cannot represent 16 as a 4-bit number. But this is what we can do. We can do that, right? 1 we can represent in 4 bits. 15 we can also represent in 4 bits. But you also know that we can rearrange the operations just a little bit, and we perform the subtraction first, then we perform the addition. Are you guys buying this? Okay. So far so good. But at this point we're still talking about arithmetic operations. Ideally speaking, if we can turn this into gate operations, that would be even better. So we look at 15 minus x. So we have 15 minus x on this side. And then on the other side, we want to look at the binary subtraction of the same thing. What is 15 as a 4-bit number? What does it look like? 1, 1, 1, 1, because it's 1 plus 2 plus 4 plus 8. Okay, so 15 is indeed 1, 1, 1, 1 in base 2. And with x, I'm going to say this is x0, x1, x2, and x3. So once again, I'm using the subscript to designate which bit of x are we talking about. Is that okay? Is the notation okay? So on the left-hand side, we are just looking at, the value 15 minus x, the entire value. But on the right-hand side, we go like, okay, let's do it in base 2. So 15 is 1, 1, 1, 1 in base 2, and an x, which is a particular value, is now broken up into 4 bits to represent its value, x0, x1, x2, and x3. Is that okay? So what do we get after this subtraction? Okay, first of all, do I have to worry about borrow? Is there any borrow of 1 in this subtraction? Why not?
Because you're taking away from max possible value of that particular digit.
Right, so arithmetically it makes sense, right? But if you remember the borrow function from previous classes, how do we define the borrow function? Okay, the borrow function applied to bit x and bit y is what?
Not x and y.
Not x and y, very good. Okay, so this is not x and y, which we write as not x times y. Okay, in this particular subtraction, what is x?
X sub 0.
X is called the minuend, which is the number that is being subtracted. They're all ones, right? This is x, 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 applied here. So the borrow is going to be what? When x is 1, the negation of x is 0. 0 and whatever is always 0. That is why we don't have to worry about borrows. Okay, cool. So what about this particular bit here? Okay, since we don't have to worry about borrows, so the result, the difference, only depends on these 2 bits. One is a constant 1, the other one is some bit from a number x. So what is this bit over here? We can call it the R of 1 comma x 0, right? That's how we define the result after a subtraction, which turns out to be the same thing as the result after an addition, which is also exclusive OR. Okay, I hope you guys do remember that part. But in this case, the exclusive OR is always exclusive ORing with 1, with true. So is there a better way to describe this? In other words, if I know that this x0 is a 0, what is the result of this?
1.
1. What if x0 is a 1? The result is a 0. Ooh, that seems like negation to me, right? So if that is negation, that means this bit is the negation of x0, this bit is the negation of x1, this bit is the negation of x2, and this bit is the negation of bit 3. Are you guys buying this? It's bitwise not, basically. Okay. All right, so once we know this pattern, then we go like, okay, so we can now go back to here, but instead of saying that this is 15 minus x, we just say this is bitwise not x. That's the tilde symbol, which represents bitwise not in C and C++. Is that okay? All right. Bitwise not, which is the tilde symbol, is really just turning the zeros into ones and all the ones into zeros when you're looking at a binary number. Okay. Oh, okay. And by the way, this operation is also called ones complement. Okay? Which means this entire thing is called 2's complement. So 2's complement of x is 1 plus the 1's complement of x, which is also 1 plus the bitwise not of x. And that is how you negate a number. Yep.
Is the numbers referring to the place value? Because the first bit is the ones place and the second bit is the second place?
Can you ask that question again?
It's like, so first complement, is that the complement of the first, of the ones place? Like the bit is for the first bit's only going to be 1 and 0, right?
Well,
and
complementing is basically negation.
Okay.
Turning a 0 into a 1 and turning a 1 into a 0, because 0 and 1 are complements of each other. So that's the reason why the bitwise not itself is called 1's complement. Now, when you add 1 to 1's complement, it is for some reason called 2's complement.
Okay.
That's just a term of the operation. So 1 plus the bitwise not of some bit pattern is simply called 2's complement.
And to me, it may, like 2 is the second place, would be the second bit. So if you have 2 of the 1 bits, then you would go to the next place, would be the 2's place, right?
I don't know exactly whether that is the reason they call it 2's complement.
Okay.
Yep. But it is called 2's complement. Okay, well, if this is 2's complement, we're going to try it out a few times and see whether it really works in general or not. So out of the number wheel of a 16-bit, a 4-bit number, pick a particular value for me to perform this operation. You can pick something that is representing a negative value, or pick something that's representing a positive value.
-5?
-5, okay. So what we're trying to do is to say, okay, we want to perform, so you want to apply 2's complement to -5. What should we get? So my claim is 2's complement is the same thing as negation. Okay? Yep, there's a, how do you call those bugs? It's not a mosquito. Mosquito hawk, okay. But it does look like a bigger mosquito. One of these days, probably not one of these days, drones will be like that size. That may be a drone already, it's just you're watching me. It's my dean, you're making sure that I'm teaching the class okay.
That's where the budget went.
Huh?
That's where the budget went.
Yep, that's where the budget went.
They just label it quote unquote administration.
Okay, so getting back to 2's complement, 2's complement is supposed to be the same thing as negation, arithmetic negation. So when you apply 2's complement to -5, what should you get back? You should get back 5, because it's supposed to be just negation. So we'll try this out, okay? So I'm going to use C2 to represent 2's complement. So we'll say 2's complement of 5 here, which is the same thing as 2's complement of the binary representation of -5. Do you guys remember what it looked like? I'm guessing it is 1, 0, 1, 1.
I think so.
Okay.
No, it's 3.
Right? Okay. So now we break it down into, okay, so it's 1 plus the 1's complement. I use C1 to represent 1's complement of that, which is 1 plus whenever you see a 0, you turn it into a 1. Whenever you see a 1, you turn it into a 0. That's 1's complement, which is also known as bitwise not. So when we are doing 1's complement to 1, 0, 1, 1, what should we get back? 0, 1, 0, 0. Okay, 0, 1, 0, 0 is the result of 1's complement. And when you add 1 to it, we get 0, 1, 0, 1 in base 2. And guess what? That is 5. So it worked. Okay, let's try something else. Let's try 2's complement on 3, positive 3, okay? And see whether it works in this direction. Yep, it's 0, 0, 1, 1 in base 2. So then it becomes 1 plus the 1's complement of 0, 0, 1, 1 in base 2. We flip all the zeros to 1s, all the 1s to zeros, so we end up with 1, 1, 0, 0 in base 2. You add 1 to it, it becomes 1, 1, 0, 1 in base 2. So if you have a copy of the number wheel, is that supposed to represent negative 3? Okay, so it does work out. Okay, so 2's complement is a way to find the negation, arithmetic negation of a binary number that is supposed to be representing signed values. Is that okay? Yes? Okay, all right, cool. So that's 2's complement, okay, which is the same thing as negation. What about this one? Last one. This one should be fun, right? What do you think it should be? What is the arithmetic negation of 0? Should be 0 itself. Okay, so we'll double check. So we write 0 as a 4-bit number because whenever you apply 2's complement, you have to perform all the operations with a fixed width. Okay, so we have to say, okay, we're going to use 4 bits to represent all the values. And that's going to be 1 plus 1's complement of 0, 0, 0, 0. And that's going to be 1 plus 1, 1, 1, 1 in base 2. And I claim that is 0, 0, 0 in base 2. Why?
0.
Where's that 1 going? Because the actual sum is actually 1 followed by 4 zeros, but because all the operations are fixed width, you do not represent the 1, which becomes bit 4. It becomes the overall carry, which is a carry out in your adder circuit, but it's not a part of the sum. So the sum itself does not represent that 1 bit. And as a result, 2's complement of 0 is a 0, so it does work out. So are we okay so far? Okay. I can see how the bug is a little distracting because it keeps flying across the screen. It likes the spotlight. Okay. So now that we understand, how negative values are represented and how to flip the sign, so to speak, of signed values, now let's go back to talk about comparison. Okay, and how do we compare? As it turns out, we have the circuitry to do comparison already, because comparison is just subtraction. But we have to look at the result of the subtraction somehow in order to figure out which number is smaller. Okay? In other words, our objective is not to come up with all the other comparison operators, greater than, less than, greater than or equal to, less than or equal to, and not equal to. Those are the operators that you use in C and C++ to relate two values, right? As it turns out, we just need one of those relations. Which one? If I just give you less than, are you guys convinced that we can implement all of the other ones using just less than? In other words, as a working, not necessarily optimal programming language, all you really need is less than. You don't need the other 5. Okay? Nobody seems to be convinced. Okay. That makes it more fun. If you guys go like, yeah, we know that already, I'll go like, ah, man. Okay. So the comparison operators or relations, one is less than, one is greater than, we have less than or equal to, greater than or equal to, we have equal to, and then we have not equal to. So most people are familiar with these operations. But if I only give you less than, does it suffice? Is it enough, just to give you less than and without the other 5?
Can we use not?
Yeah, we can use not, we can use and, we can use or.
Oh,
Okay, so we can use logical operators. So let's figure out. X is less than y, obviously we can get it done because we are given less than. Okay, x is greater than y is the same thing as y is less than x. That's a no biggie, right? We just flip the order of the comparison and we're good. X is less than or equal to y is the same thing as the negation of y is less than x. Does that make sense? Before I move on, I just want everybody to be comfortable with this one. X is less than or equal to y is really the same thing as saying x is not greater than y. Are we good? Intuitively, does it make sense?
Yeah.
Okay. So let's move on to the next one. Next one is easy. X is greater than or equal to y. We just have to flip the order of the comparison and say it is not the case that x is less than y. X is not less than y. Says the same thing. All right. So we get down to equal and not equal. Between these two, the not equal one is actually an easy one. So let's work out this one first. X does not equal to y. This one is easy if you know some other programming languages where the not equal operator is not written as exclamation point equal, and instead it is less than greater than. Because the other way to say that x does not equal to y is to say that x is less than y or x is greater than y. Okay, so we'll write it out. Okay, so we'll write it out the same way as the other ones. So this one is basically saying x is less than y or y is less than x. The plus again is representing disjunction, representing or. Okay, so if we know how to get to x does not equal to y, can we represent x equals y? Yep, just flip that. Okay, so x equals y is the negation of x is less than y or y is less than x. Cool. So after all, we don't really need the other comparison operators. Hmm? And if you remember from really early on, we also do not need negation and disjunction, and we don't have conjunction here, because those can also be done using NAND. So a really bare bone programming language can get away with less than and NAND. Although I would have to program in that programming language. But if you are talking about is it sufficient? Yes. If you can find out whether a number is less than another number, then we can do all the comparisons that we need to do in normal programming. Is that okay? All right? So from now on, our objective is to say, can we figure out whether something is less than something else? That's all we need, because once we can figure that out, the rest are pretty easy to figure out. Is that okay? All right. And I did mention that you can use subtraction for that purpose. So we'll do a subtraction, and I'm not going to tell you whether they are signed or not. We'll just blindly do the bit pattern subtraction, and then we'll figure out, okay, so if we're dealing with signed comparison, what is supposed to be the result? If we're doing unsigned comparison, what is supposed to be the result? Is that okay? All right. So we'll start with the confusing. No, let's start with something that's not confusing. 0, 0, 0, 1 minus 0, 0, 0, 0. Okay. So we have 0, 0, 0, 1 as the difference. I'm not even going through the whole, subtraction thing, with an overall borrow of 0. Does that make sense? Okay. And with this one, is 1 less than 0? No. Okay, one person said no. Are you guys convinced that 1 is not less than 0? Okay, sure hope so. Okay. And in this case, the borrow bit, the overall borrow, which is this one, is a 0. Does that make sense? It makes perfect sense. Because when you have enough, then you don't have to borrow. But having enough also means that your minuend, which is the first number, is not less than the second number, which is also called the subtrahend. Is that okay? And also in this particular case, whether you are dealing with signed or unsigned values doesn't matter, because 1 is represented as 0, 0, 0, 1, 0, 0, 0, 1 as a 4-bit number, and 0 is represented as 0, 0, 0, 0, regardless of whether you're dealing with signed versus unsigned representations. Does that make any sense? Okay. What about if I flip them? Okay. 0, 0, 0, 0 minus 0, 0, 0, 1. What is that going to look like? Without going through the details of the subtraction, I'm going to give you the answer. So you end up with 1, 1, 1, 1 with a borrow of 1. Does it make sense when it is signed? When it is signed, 0 minus 1 is negative 1. Is 1, 1, 1, 1 representing negative 1 as a 4-bit number? That makes sense. Okay. Does it make sense if it is unsigned? If we're only looking at the unsigned values represented by these numbers. 0 minus 1 is 15 with an overall borrow of 1. That borrow of 1 is borrowing a quantity of what? 16. So you have 15, but you owe 16. What is your net? Negative 1. So it still makes sense. Okay? But we are not focusing on the values anymore. We are now trying to figure out which one is smaller. Is the minuend, the first number, less than the second number? Now we have a little bit of a problem. Okay? The borrow bit is okay, can be used to indicate ordering, but only for unsigned values. Okay? So let me write it down here. So the borrow is a 1 if and only if the minuend is less than the subtrahend, but only when it is unsigned. Okay. But it is not as useful when we're dealing with signed stuff. Okay? So you look at this and go like, well, but it still works, when it is signed. Let's check out another case. Okay, let's check out this one over here. 0, 0, 0, 0 minus 1, 1, 1, 1. Okay. What do you think is the result of this? 0, 0, 0, 1 with an overall borrow. Okay? Okay, so from the unsigned perspective, is the borrow bit doing what I claim that it should be doing? The borrow bit is a 1, right?
Yeah.
But from the unsigned perspective, is 0 less than the value represented by 1, 1, 1, 1, which turns out to be 15? 0 is less than 15 is true. Yeah. Okay, so it works. But it doesn't make sense. If you look at the borrow bit, it doesn't make sense from the perspective of signed representation. Because 1, 1, 1, 1 is representing the value of negative 1 from the signed perspective. So that means we cannot use the borrow flag or the borrow bit, the overall borrow, which is this one here, to indicate ordering for signed values. We can use it for unsigned, but not for signed values. Is that okay? Okay. Let's try a few more examples. Okay. Let's try this one. 1, 1, 1, 1 minus 0, 0, 0, 0. Okay, you guys probably can figure out the answer to this one, right?
Just
1, 1, 1, 1 with an overall borrow of 0. Okay. Okay. So does the overall borrow indicate ordering from the perspective of unsigned interpretation? Unsigned. So using this statement here, the borrow flag is a 0. What is it indicating?
The mini one is greater than the subtrahend.
Not less than. That's all it's saying. It's not less than. But you're correct. Okay, we are basically, because the borrow flag is a 0, this particular rule is saying, oh, 1, 1, 1, 1 is not less than 0, 0, 0, 0 from the unsigned perspective. Does that make sense? Yeah, because 1, 1, 1, 1 unsigned is representing 15. 15 is not less than 0. 15 is less than 0 is false, and that's why the borrow flag is a 0. So it works, okay? What about from the signed perspective? 1, 1, 1, 1 is representing the value of -1, and -1 is less than 0 is true. So the borrow flag doesn't work out this time. So the borrow flag, once again, is only useful as an indicator when you're dealing with unsigned comparison. So what about signed comparison? Okay, because what is going to work in this case? Okay, so now I'm going to throw in what we call a sign bit. Okay, the sign bit is also what we know as the most significant bit. So in this case, the uppercase versus lowercase is intentional. Most significant is uppercase, but this B is intentionally a lowercase to emphasize we're dealing with most significant bit instead of byte. Okay, if it's uppercase B, it is usually byte. If it's lowercase b, it is bit. Most of you know this already because when you look at your internet connection, the quote-unquote bandwidth, it is measured either in megabits per second, with a lowercase b, but when it's measured in megabytes per second, it's an uppercase b. Okay. So the sign bit is known as the most significant bit. So if I were to identify every single most significant bit, it'll be this one, this one, this one, and this one. Every 4-bit number has a most significant bit being bit 3, because we have bit 0, bit 1, bit 2, bit 3 is the most significant bit of a 4-bit number. Is that okay? So we look at this and go like, can we use the sign bit to indicate the ordering of two numbers from the signed perspective? What do you think? You look at these 4 cases, does it work? Well, we'll try it out. Look at the first case. 1 minus 0 is a 1, and from the signed perspective, 0, 0, 0, 1 is still representing the value of 1. 0, 0, 0, 0 is still representing the value of 0. So the sign bit being a 0 seems to be okay. We look at the next one, this one here. Does the sign, if I use just the sign bit of the result of the difference, does it seem like it's working? It can indicate the ordering between the minuend and the subtrahend. It seems to work too, because 0, 0, 0, 0 represents 0, even in signed representation. 0, 0, 0, 1 is representing the value of 1, even in signed representation. 0 is less than 1 is true. The sign bit is now a 1. So it seems like the sign bit can in fact be used to indicate whether the minuend is less than the subtrahend in signed comparison. It seems like it's just a duplicate of the borrow flag, right? 1 and 1, 0 and 0. Okay. Let's check out the bottom 2 cases and see whether they work out or not. 0, 0, 0, 0, sign representation is of 0. 1, 1, 1, 1 is the sign representation of negative 1. 0 is less than negative 1 is false. Ah, the sign bit says 0. Seems good to me. And then we look at the last case. 1, 1, 1, 1 is the sign, is the representation of negative 1. 0, 0, 0, 0 is the representation of 0. Negative 1 is in fact less than 0. And the sign bit is a 1. Well, looks like it's working in all 4 cases. So what is the problem? Okay, so I'm going to write a summary here first, okay? It seems like the sign bit can indicate ordering of signed comparison. And it makes sense too, because when you do a subtraction and the result turns out to be negative, doesn't that tell you that the minuend is less than the subtrahend? Yeah, so it seems to make sense. Unfortunately, it doesn't work all the time. Okay, so let's take a look at some cases where this is not going to work. And you guys can tell me what is the pattern when it stops working, okay? Because there's a certain pattern to it. Let's try 0, 1, 1, 1 minus 0, 0, 0, 1. Okay? And remember, we are focusing on signed representation now. Forget about unsigned representation. So what is this going to look like? Well, this one will work. Never mind. Sorry about that. I'm going to delete this until we get to 1, 0, 0, 0 in base 2 minus 0, 0, 0, 1 in base 2. And what do you think the result is going to be? Well, we'll do some quick calculation here. And this time I'm going to go for the whole thing. 0 minus 1, okay? 0 minus 1 is 1 with a borrow of 1. Okay? And then we have 0 minus 0 is a 0. But then 0 minus 1, oh, I forgot to write this one first. But then 0 minus 1 is a 1 with a borrow of 1. Is that making any sense? And then we got 0 minus 0 is a 0 again. And then we have 0 minus 1 being a 1 with a borrow, right? And then finally we have 1 minus 0 is a 1. And then 1 minus 1 is a 0. And there's an overall borrow of 0. Is that okay? Let me look at this, go like, but it doesn't work anymore. The sign bit alone is not indicating whether the minuend is less than the subtrahend. What is the sign bit of the difference this time? Which bit are we looking at? What is the most significant bit of the difference? It's a 0, okay? So if this were to work all the time, that would have indicated that the minuend 1, 0, 0, 0 is not less than, because it's a 0, is not less than the value represented by 0, 0, 0, 1. But in reality, what is 1, 0, 0, 0 representing on the number wheel? It's as negative as it can get, right? It's negative 8. So if we just look at the sign bit, it is saying negative 8 is not less than 1. That doesn't make sense. Are you guys following? Okay. Okay. Let's figure out another case where this doesn't work. Okay. So this time we got this. Okay. Okay. So let's check this one out. Okay, 1, 1, 1, 1 minus 0, 1, 1, 1. They're all in base 2. we'll carry out the actual subtraction first, but this time I think I don't need to do the full subtraction because there's no borrow, right? Is it obvious to you that there's no borrow in this case? Because for every single digit, the digit of the minuend is at least as big as the digit of the subtrahend. So there's no borrow in this particular subtraction. So I'm just going to make a quick subtraction here. 1 minus 1 is a 0, 1 minus 1 is a 0, 1 minus 1 is a 0, 1 minus 0 is a 1, with an overall borrow of 0. And remember, since we're only focusing on signed representation, the borrow doesn't really matter in this case. I'm just putting it here just so that for completeness. Okay? Is the sign making any sense? What do you think? It is making sense again, because 1, 1, 1, 1 is representing negative 1, 0, 1, 1, 1 is representing 7, negative 1 is less than 7 is true, and the sign flag is 1. So sometimes it works and sometimes it doesn't work. What is going on here? What do you think? What do you think is going on here? Let's try one more case, okay, where it does not work. So with this time we have 1. Oops. Okay, so we have 1 0. Okay, maybe 1 1 1 0 minus 0 0. Oops. Okay, 0 1 1 1 in base 2. So it really is just one off from the previous case. But this time it is not going to work. So let's find out what is the result of this subtraction. What do you think is going to be the result of this subtraction? This time it does have some borrows. So I'm going to do the full subtraction just as an exercise. 0 minus 1 is 1 with a borrow. Okay, so we put a 1 here and put a 1 here. And the 1 minus 0 is a 1. Okay. And then we got 1 minus 1 being a 0. But then 0 minus 1 is a 1 with a borrow. So we have 1 as a result, 1 as a borrow. Once again, 1 minus 1 is a 0. And then 0 minus 1 is 1 with a borrow. So we've got 1 here and a borrow here. And then we have 1 minus 0 being a 1. And then 1 minus 1 being a 0 with no overall borrow. You look at this and go like, oh, now it doesn't work again. Because 1 1 1 0 sign is representing negative 2. 0 1 1 1 is representing 7. But the sign bit is saying 0. So the sign bit if we were to rely on just the sign bit, it is telling us that negative 2 is not less than 7. That's not right. So we cannot rely on the sign bit alone. But in order to understand why it is not working reliably and to fix it, we have to understand why it is not working. How is it not working? So now we can focus on the values. Okay? So in a signed subtraction, if you look at all the cases where it does not work, okay, this one doesn't work, this one doesn't work, right? What is common to the cases where it does not work?
Right at the end, it's 7.
From the value perspective, okay, when you look at the value of the sentence, is it correct? And are we getting the right result? Are we getting the right difference with the cases where it does not work? They're not.
Oh.
This is negative 8 minus 1 it should give us negative 9. But we cannot represent negative 9 as a 4-bit number. So instead of getting negative 9, we are getting 7. So that's wrong, okay? But this one is the same situation. We start with negative 2, we subtract 7 from negative 2. We should end up with negative 9. But what do we end up with? 7. It doesn't work. But it doesn't work because we don't have enough slots on the number wheel. We just cannot represent the result is out of range. Okay? In both of these cases, they're out of range from the perspective of we don't have enough negative values. Do you think we can make it not fit on the other side as well?
Yeah.
Okay, and how do we make that work? How do you end up with a positive number that is too big in a subtraction?
Subtract a negative number.
Subtracting a big negative value, right? Okay, very good. We'll try the simplest way to do it. Okay, because 1000 is representing the most negative value we can represent, which is -8. So from the perspective of a signed subtraction, 0 minus -8 should be 8. But we know 8 cannot be represented as a 4-bit number in signed representation. But we want to find out exactly what's going to happen with this subtraction first. So we'll go ahead and carry out this subtraction. And this one is pretty easy. It does have one borrow, but it's only the most significant bit. 0 minus 0 is a 0. 0 minus 0 is a 0. Okay. Easy peasy for the least significant bit. 0 minus 1 is a 1 with a borrow. 1 minus 0 is a 1. So that's the final result. Oh, it's also given us the wrong answer, because it is saying that the sign bit being 1 is, if I was right in the beginning, then it is telling us that 0 is less than -8, which is wrong. So we can be wrong the opposite way. Okay, the sign flag is a 1, but it is not less than. Is that okay? So the reason why the sign bit alone is not enough is because we can overflow what a 4-bit, in this case, representation can actually represent. We cannot represent +8 as a signed number. That's the problem. Is that okay? All right. So if that is the case, maybe we need an indicator of whether the result of a subtraction is overflowing. Are we running out of digits to represent the result after a subtraction from the signed perspective? Is that okay? From this experience, how would you start with deriving that overflow flag? You can focus on just the sign of the minuend, subtrahend, and difference. Forget about the rest of the digits. Okay, if you focus on just the sign bits of the minuend, subtrahend, and the difference, minuend, subtrahend, difference, that alone can tell us whether the result is overflowing or not. Okay, so let's go back to the sign bit. So the sign bit can only be a 0 or 1, but it is called the sign bit for a reason. If the sign bit is a 0, what type of value are we representing? The rest of the bits can be whatever, okay? But we just need to categorize what it is. If the sign bit is a 0, the value the number is representing has to be
Positive.
non-negative. Okay, we call it non-negative because 0 is also in that set. Okay, if the sign bit is a 1, what are we representing? Negative values. Okay, so from that perspective, it looks like we got a pattern here. Okay, let's figure out, the 4 possible ways to do it. There are 8 possibilities. Okay, so I'm going to use a truth table for the 8 possibilities. I'm going to use M to mean the most significant bit. Okay, maybe MS. Okay, the sign bit of the minuend, the sign bit of the subtrahend, and the sign bit of the difference. Is that okay? So M for minuend, S for subtrahend, and D for difference. And then the subscript S is for the sign bit, which is also known as the most significant bit. Okay, so this truth table is going to have 8 entries. Okay, 1, 1, 1, 1, 0, 0, 0, 0, 1 1 0 0 1 1 0 0 1 0 1 0 1 0 1 0. Okay, and I want you to tell me whether there is an overflow or not after subtraction. After subtraction. Okay. So what you need to do is now to look at the most significant bit known as the sign bit, and not to think of it as 0 and 1, but think of it as negative, 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 non-negative, and so on. So you have to tell me whether the result after the subtraction, whether the difference is making sense or not. So we'll start with row 1. You have a negative value, you subtract a negative value from it, and you end up with a negative value. Is it overflowing, or does it make sense?
Makes sense.
It can make sense, right? Okay, it's not overflowing. Okay, so that means it is not overflowing. Put a 0 here. Okay, next row. You start with a negative value, you subtract a negative value from it, and you end up with a non-negative value. Can it make sense? Think carefully.
Yeah.
No.
It makes sense.
Negative, negative number subtracted from that would be positive.
Can be either way,
Yeah.
right? Okay, the easiest way to look at the second row is negative 2 minus negative 2 is 0. And 0 has a sign bit of 0. Okay, so it still makes sense. Okay, not a problem. Cool. What about the next row? You have a negative value, you subtract a non-negative value from it, and you end up with a negative value. Makes perfect sense, right? Because it's just pushing the negative value further to the negative side. So it makes sense. We do not have an overflow situation here. What about this one? We started with negative value, we subtract a non-negative value from it. But then the difference, the result, is non-negative.
It's overflow.
It's overflowing. Okay,
Yeah.
so we have an overflow condition here. We put a 1 in this on this row. Okay. Let's see. Okay, just for my own visual thing, I just need to draw some horizontal lines because otherwise I lose track. Okay, so now we have 0, 1, 1, which means we have a non-negative value, we subtract a negative value, and we end up with a negative value. Does that make sense to you?
No.
It does not make sense. Okay? Because when you subtract a negative value, it is the same thing as adding something, right? If you're adding a positive value to a non-negative value, it should not push you to the negative end. So it doesn't make sense, which means we have an overflow situation. So without spending any additional time, I'm going to just tell you the rest are all zeros. Okay? Like so. Okay, so we have now a truth table corresponding the most significant bits of the minuend, subtrahend, and difference to whether it is overflowing or not. So if I call the overflow flag O, okay, in some text, they call it V because O looks like a 0, which is kind of confusing. So in some textbooks or in some architecture, this is known as the V flag because they choose the second letter of overflow to represent overflow. But I use O, uppercase O in this class. If you want to avoid any confusion, you can always say OV for overflow. Okay. So if I were to find out a logical equation to figure out the overflow flag, what do you think that should look like?
Not MS and SS and DS,
Mm-hmm.
or the exact opposite of that.
Okay, so we'll spell out the exact opposite. MS and not SS, not and not DS. Is that making any sense? Because we only got 2 rows that actually end up with a 1, right? So if we can have one conjunction to generate one, of these rows, and have another conjunction to generate the one for the other row, then we are done. So the first expression, or the one to the left of the disjunction, is going to handle this one. Because when MS is a 0, not ms is going to be a 1, and then ss and ds are non-negated. So when you have a conjunction of 3 ones, you get a 1. So that takes care of this one here. The expression to the right-hand side, or the second conjunction of the disjunction, takes care of the 4th row of the truth table. Because when ms is 1 and ss is 0 and ds is a 0, then you have to negate ss and ds before you do the conjunction. Then you once again have 1, 1, and 1, which means the result is a 1. Is that okay? All right. Okay, so let's apply this to the earlier examples and see what we are going to get. So what we roll back to all of the examples that we have done so far. And then what we'll do is we'll say, what is the sign flag of this guy? Sign flag is a 0. Okay. What about the overflow flag? The overflow thing, remember the equation? Okay. Or you can just look at the values and tell me whether it's overflowing or not. Is it overflowing? Nope, it's not overflowing. What about this one? Sign flag is a 1, but we are not overflowing. Is that okay?
Yep.
All right. What about the third one down here? What about this guy? The sign flag is a 0. Is it overflowing? It is not overflowing. There are only 2 patterns of overflowing, which is 1, 0, 0, and 0, 1, 1. This doesn't fit that pattern. You know, if you have a pattern like 1, 0, 0, it is overflowing. If you have the pattern of 0, 1, 1, it is also overflowing. This is not one of those patterns. So we don't have overflow. What about this one here? The sign flag is a 1. Overflow is a 0. We do not have overflow. Are we still doing okay? More or less? All right. Moving on to the trickier cases. Okay. So now we look at this one here. Are we overflowing? Okay. The sign flag is a 0. The overflow is a 1 because we have one of those patterns. This one fits the pattern of 1, 0, 0. Because we're only looking at the most significant bits or the sign bits of the middle end, upper end, and difference. So we got 1, 0, 0. It is overflow. Okay. What about the one to its right? Sign flag is a 1. Overflow is
0.
a 0. Okay, very good. The one over here, we have a sign of 0 and an overflow of 1. Okay, very good. And this one has a sign of 1 and an overflow of 1 as well. Okay. So it looks like we got all of the possible cases, right? Because the sign flag is 1 bit, the overflow is 1 bit. Out of 2 bits, we end up with 4 possible combinations. 0, 0, 1, 1, 0, 1, and 1, 0. And we have seen them all. Do you notice any pattern? Okay, so let's add something on top of all of this. Let's actually add less than, okay? Is it less than or not? Okay, so we'll go from the earlier ones again. Okay, so with this one, is 1 less than 0? No, right? So we'll say less than is 0. Okay, this is not less than or equal to. It means less than is false. Is that okay? I just want to make sure that we are not confusing this symbol to less than or equal to. We are simply saying that less than is false. What about the one to its right? Less than is true. Okay, because 0 is less than 1. What about this one here? Is 0 less than -1? No. What about this one over here? Is -1 less than 0? Yes. Okay. And then we move on to the next page and continue with this. Okay. This one is asking, is -8 less than 1? Okay, yes. Is -1 less than 7? Okay. And this one is asking, is -2 less than 7? Okay. And then this one, the last one, is asking, is 0 less than -8? No. Okay. Okay. What do you notice out of the examples that we have kind of touched on?
NAND.
Not exactly.
Oh, exclusive OR.
Exclusive OR is the right answer. Okay. In other words, whenever the sign and the overflow do not agree, it is less than. When they do agree, it is not less than. Right? Okay, let's check it out. They agree, not less than. They do not agree, it is less than. Do not agree, it is less than. Do not agree, it is less than. It doesn't matter which one is a 1 and which one is a 0. If they disagree, it is less than. So far, so good, right? And then we go back here, and we look at these, the earlier examples. Does that rule still hold true? They agree, not less than. Not agree, less than. Agree, not less than. Disagree, less than. Cool. So I think we finally got the indicator of a signed comparison. So I'm going to move all the way back here, and basically I'm going to use I'll use the L flag to mean less than. So the L flag is defined to be the sign flag, exclusive OR with the overflow flag. So this sign flag here is what we call DS in our discussion. It is the sign flag of the difference. So the sign flag of the difference, exclusive OR with the overflow flag, is the L flag, which indicates the L flag is a 1 if and only if the minuend is less than the subtrahend in signed interpretation. Okay, let me just write it down here. So the L flag is a 1 if and only if the minuend is less than the subtrahend. But this time we are talking about signed comparison. So are we doing okay with this stuff here? Yes? Kind of? Maybe? Okay. But I have a problem with this lecture, the entire lecture today. I never gave you a proof. This is all by observation, right? I just threw a few examples on the whiteboard or the projector, and said, okay, let's observe. Let's try to find some patterns, with these things, and we figure out something. Okay, we seem to figure out, hey, we got the L flag for signed comparison, and we have the borrow flag for unsigned comparison. So far, we have not found a case where it does not work. But does that mean that it's going to work all the time? No. So what are we going to do? Okay, let's check out the notes. Some of you will absolutely not like it. Okay, binary number comparison is where we are at this point. And those of you who do not like math will not like this. Now I have something to say about people who want to program but do not like math, but we'll wait a little bit to get to that part.
It's basically basically a discrete math course a little bit.
Yes. So basically, I have these proofs. Okay, so down here, these are all basically proofs to show that the rules that we laid down today, the borrow flag is a 1 if and only if the unsigned comparison yields a less than. The L flag is a 1 if and only if the signed comparison yields a less than. So I actually have proofs to show that that math does work out. Okay, so this is for signed comparison, and if you look at this math here, this whole thing is a proof. Okay, not the whole thing, but up down to here. That's the representation, and then when we get down a little bit further, there's a little bit of a proof to show that in general that rule does work. How important are these proofs? Not in the context of this class, but in general. What do you think? It is very important, okay? And before we end today's class, I got 2 more minutes. Remember, I said something about people who do not like math but want to program? Okay, so the question is, there are 2 questions. The first question is, can you still program if you do not like math?
Yeah.
The answer is yes.
Won't be very
The
good.
second question is, can you program effectively when you do not like math? And the answer to that one is going to be kind of questionable, okay? It's kind of like, do you guys think I can play basketball?
Yeah.
A little.
I'm able, okay? I got at least one arm that can swing, right? And I'm mobile enough to walk around. So I can shoot a basketball at some place. But is it gonna land in the hoop? Maybe, out of 100 times, right? I'm gonna get it once or twice.
You're lucky you could hit the backboard.
Now you put me in a scenario where everybody is like 6'5", athletic, fit, young, mobile, quick on their feet, quick on their head. Do you think I can score a single point in any game?
You might.
Well,
If you
I
believe
might
in
get
yourself.
I might get a pity point, right? It's like they might lift me and go like, just drop the ball here, you might get a point. Okay?
Wow.
And that's the opposing team, right? Just holding me up, go like, Tag, you need 1 point. Come on, do it.
You'll win the game if you're a strange dad.
So just because I can do it doesn't mean I'm going to be good at it, right? It's the same thing with math and programming. Because computer science really is a branch of math. Do you guys know that?
Applied math.
Makes sense.
Hmm?
It makes sense.
It makes sense because it's all made up rules, right? They call it computer science because it is not a science. Think about all the terms, all the fields that has a science in it. Political science, is that a science? No. Computer science is not a science. Why is it not a science? I know we're a little bit stretching out that. Why is computer science not a science? Why is math not a science? What is science? What we talked about really early in today's lecture, right?
Observation.
Quantum physics. Physics is a science. Chemistry is a science. So what differentiates, what is the difference between physics, chemistry, quantum physics, astronomy, versus math and computer science and statistics?
Because physics and chemistry and all that are observations of patterns in the real world, while in the world around us, while math and computer science are just patterns that we found.
It's actually a little bit worse than that. In one case, we are trying to figure out the laws of nature. In the other one, we are defining the laws. We are saying, if you write this code, it's going to do it this way. So we are actually defining all the rules. Okay, in math, in computer science, in statistics, in all of those cases, we are the ones making up the rules. Now, are those rules actually useful? Yes. Do they model a lot of things in real life? Yes. But are those made up rules?
Yeah.
Absolutely yes. Okay, so they're completely different. Okay, I have to dig up one of the pictures that I saw, many years ago. So it's kind of like a class setting like this, and one of the students, is writing on his or her own note saying, why the F am I, studying math in this class? I just want to do some game programming. Now, game programming is a different thing. Okay, if you know anyone in the game programming industry, you will know that game developers, what kind of work condition do they work in?
Stressful.
Stressful.
Why is it stressful? If you're the super hot shot and the company cannot do without you, why would you be stressful?
Because they work on little bus cycles.
Exactly, they're a dime a dozen. In other words, they're grinding. just like some people have to grind to get points and whatnot in the game, game developers, for the most part, not all of them, but many of the game developers are basically grinders. And if they're grinders, that means, hey, if you don't like this job or if you want to get paid more, there's always the next person to come in. So where are the high-paying jobs where people say, oh, Tech, we don't want to fire you. You want a raise? Sure, we'll give you a raise right now. What type of job has that nature?
Silicon Valley? Yeah.
Well, Silicon Valley, but what line of work is going to be of that nature?
Design.
Design,
Maintenance.
computer security.
So,
If you're a top-notch forensics expert, if you're a top-notch, counter-hacking kind of expert, they are gonna say, well, if you want to be paid more, we'll pay you, because we don't want you to work for the other team. Do you see where I'm going? And guess what computer security has?
hackers.
Lots of math.
Yeah.
Encryption is all about math. Yep, and there are a lot of other stuff like statistics. There's a lot of statistics in computer security. Why do you think statistics is useful in computer security?
Predictions.
Predictions and identification of intrusion. Things that are out of the ordinary. This usually doesn't happen this way. This person never types like this, or never make mistakes like that, or never execute commands in this particular sequence. Each event on its own doesn't seem to be a problem, but the sequencing of these events is going like, this is highly unlikely. This is very unusual because this person usually does not do things like this. And that's when statistics becomes handy.
That's how the I'm Not a Robot trackers work, is they track your mouse movement for like 30 seconds, and then if you move like you normally do, then you're a human. If you're jumping all over the screen, then you're a robot.
Yep. So, okay, so I think I have done enough discouragement for the night. You guys can stay here when I'm adding the activity to Canvas, or you can go outside and get some fresh air, but we'll get the lab portion started in about 7 minutes.
Not too discouraging, not too discouraging. And I like math, it's just I got a bad grade once. Okay, twice, but I got an A when I got that.
Math, to take a math class, to do it successfully, a lot of times you have to see the application. Because otherwise math can be super dry, and I don't like that either. I don't like anything that's super dry and I don't see the application. But when it has an application and you're going backwards to figure out, how do I get this? How do I mathematically model something? Now it's a lot more fun because now you have an objective that you are actually trying to accomplish. This is really a means to an end.
Yeah.
Yep.
What I really enjoy about this class, though, is that I always wondered, how do computers start? It wasn't just like, oh, we instantly have processors. I get to see the beginnings, the origins.
Well, and also how these equations and whatnot are derived.
Yeah.
Because I'm not just telling you, oh, this is what it is. Just take it.
No.
I want you guys to think about it and go like, why does that work? Or how do I make it work? All right. I'm just gonna import. I have to copy the quiz from the other class, so that takes me just a minute.
Cool.
Okay. But there are always a few people who find the discussion today discouraging. It's like, oh, you just shot my dream. Okay. Import. Select. Okay. Do. Part 2. Okay.